Okay, so we're given some data on hospital births. So this histogram displays the results of a simulated year of births for a hospital that has 50 births every day. So what the data represents is the number of girls born out of those 50 every day. And we know that the mean of the number of girl births is 25.06. So the mean's right about here. And that makes sense that it's in the middle. It's a symmetric distribution, and we're talking about the mean is 25.060, and the spread is about 3.472. So an example would be, what does this bar of the histogram represent? What this is telling me is that there were 9 times that 30 girls out of 50 were born in the hospital. So that would mean that there would be 20 boys out of the 50. So that happened 9 times. Over here, there were 7 occasions where only 19 of the average 50 girls were born. So since this is a simulated year, these frequencies actually represent the days. So altogether, if you add all these frequencies up, you're going to get 365. So n is 365, which is the number of days in the year, so the number of days that we counted the girl births. So with this information, we can go forth and figure out how much of the data is within a certain distance from the mean. So for part A, we want to know how many girl births are 1 standard deviation below the mean and how many are 1 standard deviation above. So what we do is, with the mean being 25.06, I'm going to use green now. So we take 25.060, and if we subtract the 1 standard deviation of 3.472 girl births, that will give me, Mars?
21.588.
21.588 girl births per day. Girl births are in that day. So 21.58, let's see, let's get this, is going to be bigger than 21. So I'm just going to put it in between 21 and 22 and not including 21. Because 21.5 is bigger than 21. So that gives me a lower boundary on the left. And if I take the same equation, but if I want to go above the mean, I get 25.060 plus 3.472. That'll give me, Mars?
28.532.
28.532 girl births. So that's 28.5 is above 28, but less than 29. So that gives me my upper fence to be right about there. So if I want to know the percentage, so now I'm on part B. If I want to know the percentage of girl births that were within 1 deviation from the mean, 1 standard deviation. So here's 1 standard deviation above, here's 1 standard deviation below. So within 1 deviation, what I now have to do is take these frequencies and add them all up. So this is how much of the data is within these 2 limits. And when I add those numbers up, I get 245. And then 245 out of 365 gives me approximately 67.1%. So what we just found is, in the simulated year of births for this hospital, 67.1% of the days were within 1 standard deviation of the mean. So 67% of the data were between 21 girl births, or 22, I should say, girl births, and 28 girl births. For part, I believe C or D, or we're going to move on and take this even further. So that was just 1 deviation away. I'm going to erase these so it doesn't get too crazy. I'm going to leave the limits though, just because they're nice to see here. So there's my limits of my 1 deviation away. And now if we go for 2 deviations above, again, how do I find 2 deviations above? I just take 25.060 and I either add or subtract 2 standard deviations from it. It's getting a little crowded here, but I think you can get the gist. So the upper 2 standard deviations above that mean will be what, Mars?
32.004.
32.004, which is still higher than 32. So I'm going to include the 32s and leave out the 33s. And then on the low end, 2 standard deviations below is
18.116.
18.1. So that doesn't include the 18s, but it does include the 19s. So there's my 2 standard deviations. 1, 2 standard deviations above, and 1, 2 standard deviations below. And now if I were to want to know how many of, what percentage of births occurred within 2 standard deviations of the mean, again, I'm adding up all these along with the ones I had before. It's actually easier. You know the total is 365. It's actually easier to subtract the outer frequencies. And I think I end up with, Mars, not 245. 348. You end up with 348 out of 365. Again, this is like part C. And that's approximately 95.3% of the data. So notice in a symmetric distribution, when you go 2 standard deviations out from the mean, you're getting 95.3% of the data. That's a lot of the data. Your chances of being within 2 standard deviations of a mean is pretty darn high. Cool? So we've done 1 deviation away, 2 deviations away, and finally, I'm going to clean up the board a little bit, and then we'll get to 3 deviations away. So we'll do the same thing. In fact, while I'm erasing, you should be finding your boundaries for 3. I'm sure you can do it. What do we go? Do we go red for this one? Or, yeah, let's go red. Have you found him? Have you found him, Mars?
Yeah.
Good work. Okay. So Mars knew that to find the 3 standard deviations away, you take 25, your mean of 25.06, and you either add or subtract 3.472. You add to get the high upper deviations and you subtract to get the low. So the upper deviation was what, Mars?
35.476.
35.476. So again, my boundary is going to be above 35, below 36. I might even write that in there. 35.476. And then the lower boundary was
14.644.
14.6, so that's way down here. 14 off the scale, 644. So notice 3 deviations away from the mean. 1, 2, 3 above and 1, 2, 3 below. That's going to give us the bulk of our data. There's only 2 days out of the year where we had girl births that were outside that range. So that means that our percentage of data within 3 standard deviations of the mean is going to be 363 out of 365, which is approximately 99.5%. Look, very close to 100% of the data within 3 standard deviations. So once again, if you want, let me show you again. Let's give the boundaries. This was 18, the lower for 2 deviations, 18 point, help me out, Mars. 116. And then the upper was
32.004.
32.004. And then in for the first deviation, 21.588 and 28.532. So there's your fences. And again, we use those fences to figure out what percentage of the data is within a certain number of deviations. So now you can do the placement scores. Enjoy. See you tomorrow.